Hello, we group 3 will present about scalar modeling of acetaminophen production reactor. Here is our index. Acetaminophen, widely used for antipyretic and analgesic, is essential for alleviating pain and reducing fever in various medical conditions worldwide. In 2021, when the COVID was worldwide spread, estimated market size of acetaminophen was about $9.4 billion. And as expected continuing growth in the pharmaceutical industry, acetaminophen is one of the important materials. These are research data of acetaminophen market. For efficiency and profit, we decided to model scale-up continuous reactor using small-size batch reactors data. Acetaminophen is synthesized through the acetylation of p-aminophenol using acetic anhydride, forming the active compound along with acetic acid as a byproduct. And by excess input of acetic anhydride and addition of water, we can get greater product output. These are key assumptions for scale-up. First, by excess input of acetic anhydride, we will induce pseudo first-order reaction. The evidence of it will be given later. Second, because the reaction is on liquid phase, we can assume constant density and volumetric flow rates. This is concentration versus time graph from Jiang's experiment. They used 250 ml volume batch, and the amount of reactant is 0.09 mole p-aminophenol and 0.34 mole acetic anhydride. The experiment was conducted at different temperatures, and the results of rate constant are shown in the table here. And we will use K value 1.99 per minute at 353 Kelvin. For validation of the K value, we found other research paper with other size reactor. Here in Jean-Luxen's research, there is fractional conversion data in CSTR. The reactor size is 7.76 cubic meters with 3.28 kmol per minute p-aminophenol and 18.37 kmol per minute acetic anhydride feed at 353 Kelvin. Here we organize the table of the paper every 5 minutes. Using mass balance equation of CSTR, the result of calculation is like this. We can get the value 2.142 to 2.143, which is very close to the first K value 1.99. For additional validation of pseudo first order reaction, we got data like left side of slide, with approximate estimate on the graph of research paper. And we can set mass balance equation like right side. There are two cases. First, m and n both are 1, so we can assume second order reaction. And second, m is 1 and n is 0, the first order reaction. We drew two graphs using graph tool. Small b in red box is concentration of acetic anhydride. We can check the purple line of second order reaction goes close to blue line of first order reaction when the b is much larger than a. So we can assume that the pseudo first order reaction is excess input of acetic anhydride.
For the scale-up of our production, we wish to be able to cover the Korean annual consumption. So a paper from 2021 stated that this would be around 155 metric tons per year, and that was set as our scale-up output goal. For the scale-up plan, we wish to investigate 3 different configurations: one CSTR, one PFTR, and one CSTR plus PFTR in series. Here we wish to compare the reactor volumes, the residence times, and the number of processes required to reach our scale-up goal. Starting from the CSTR, we decided on a conversion of 99.9%, and this is based off of experimental work that shows this is possible. Then we were able to calculate the raw materials needed for this process, and we got the flow rates of p-aminophenol of 0.213 kilos per minute and acetic anhydride of 0.561 kilos per minute. And this ratio is also based off of experimental work. We decided on a volume of 10 cubic meters based on the normal range of CSTR volumes. Then, using the mass balance equation for CSTRs, we calculated a residence time of 8.37 hours and a volumetric flow rate of 19.9 liters per minute. This flow rate is going to be used for the consecutive processes we will cover. Then in the PFTR, the same conversion, and of course the same volumetric flow rate as I just mentioned, is used. And then using the mass balance for the PFTR, we calculate a residence time of 3.47 minutes and a volume of 69.15 liters. Then we can compare the CSTR and the PFTR process. When we have the same conversion goal, we see that the residence time is longer for the CSTR compared to the PFTR, And because the residence time is related to the volume, we also get a bigger volume for the CSTR compared to the PFTR. And this speaks for choosing the PFTR over the CSTR. However, because we want to work isothermally, that speaks for choosing the CSTR, as it is easier to maintain isothermal conditions in a CSTR compared to a PFTR. Now for the CSTR plus PFTR in series, we decided on a conversion in the CSTR for 50% and a conversion in the PFTR at 99.9%. We have the same volumetric flow rate as before, and then we're able to calculate the residence times and the volumes. The residence time in the CSTR is 0.5 minutes, and the residence time in the PFTR is 3.12 minutes. This gives a total residence time of 3.63 minutes. The volume of the CSTR is 10.01 liter, and the volume of the PFTR is 62.21 liters.
We compared the residence time and reactor volume of the three reactors, and as shown in the table, the results follow the order of CSTR, mixed, and PFTR. Next, I will discuss the pros and cons of continuous reactors compared to batch process. Continuous reactors enhance process efficiency and increase the IRR. However, a notable drawback is the difficulty of quality control. From a cost perspective, we evaluated the production of 155 tons of acetaminophen annually using CSTR as a baseline. Since all three reactors use the same inlet conditions, the raw material costs are identical. Therefore, cost differences arise from operational expenses, where larger volumes and higher process frequencies result in increased maintenance costs. Consequently, the cost order is PFTR, mixed, and CSTR. In this study, we analyzed and compared the CSTR, PFTR, and mixed continuous process to optimize and scale up acetaminophen production, evaluating both economic feasibility and operational efficiency. Using existing research data, we applied the reaction rate constant to model residence time, reactor volume, and heat generation. Based on Korea's annual consumption target of 155 tons, we proposed an optimal design for large-scale production. While PFTR demonstrated advantage with its smaller volume and shorter residence time, it also incurred higher heat management costs. To address this, we suggested a hybrid model as a more suitable alternative. However, the assumptions of idle conditions and the lack of detailed maintenance and heat control cost analysis for PFTR highlight the need for further research for practical implementation. Thank you for listening to the speech.